Make sure that you check out the Piazza post on how the last 2 weeks will work. Some of the due dates have shifted, and of course the lab and hack sessions will still be held. You'll use those to redo a hack, or up to 2 hacks, and up to 1 lab among labs 5 through 12 or something like that. The details are in the post for reconsideration. There will be a final exam during the final exam date. The details are still to be determined, but there will be a multiple choice part, I think 20 questions or so, as well as a programming exercise part. Okay. Again, more details after I get a learning assistant to review and edit my submission. All right, just making sure that it works. So we stopped off with talking about binary search, and we implemented it, and we saw, and we analyzed it, and we saw how much of an improvement it was, right? It's an exponential speed up over linear search, right? So, but the problem is that it requires that you're able to jump to the middle index. So in other words, you're working on arrays. Sets, not so much. It's not going to work that way because it's not ordered. And of course, it requires that the search criteria be exactly the same as your sorting criteria, which means that it needs to be sorted. Because for that assumption that if you look at the middle element and everything over here is less than that element versus everything over here is greater than that element, that is only true if the entire thing is sorted. Right? So that means that we have to come up with some sorting algorithm. We briefly did that last time by saying, okay, well, 4 is the first element, right? And so I'm going to go through this and I'm going to find the element that belongs first. And all we did was, 4 is not it, that's not it, that's not it. Okay, there, 1, and then I put 1 at the beginning. What I did is I went through and I selected the minimum element and I put it at the beginning. Then I went through and selected the second minimum element and put that in the second spot, the third spot, the fourth spot, etc. Right? And I emphasize the word selection there because that's what this is called. This is selection sort. Right? So the basic idea, again, is that you go through and you find the element that is the smallest one, right? So here's the basic idea. Find the minimum or minimal, right? Because there could be multiple values, right? If 1 is the minimum value and there are three ones, they all belong at the beginning, and there's no way for you to distinguish between those 3 different ones. Find the minimum or minimal element and place it at the beginning. Right? Now, of course, we're assuming that we're sorting in ascending order here, non-decreasing order. Then go through the remaining n minus 1 elements, find the minimum, and place it at the second place. Right? In general, on the ith iteration, the elements 0 through, I'm going to be using 0 indexing here, 0 through I minus 1 are already sorted. Right? So what do you do with the remaining elements, I through n minus 1? Right? And so let's visualize that. I'm going to come over here to the pad over here. And again, what I'm going to do, I'm kind of thinking inductively. What I'm doing is I'm jumping into the middle of the algorithm. The beginning of the algorithm, that's pretty clear because you go through the entire array, find the minimum, and you put it at the beginning, right? But what happens when you need to generalize this because you need to write a loop to do it, right? So what you're going to do is you're going to assume that the elements not A1, A2, and I'm just going to go ahead and jump to 0 indexing here, through A sub I minus 1 are all sorted. And so I'm going to leave that alone, sorted. Ignore, right? Because if you're going to muck with any of that stuff, then it's already, everything there is already where it needs to be. If you perturb that or muck with it, right, then you're putting something out of order, right? So again, this is the ith iteration. The remaining elements, ai through an minus 1, again, 0 indexing, these are unsorted. So now think about this general case where you've already jumped to the ith iteration of this loop. What are you going to do now? Among elements I through n minus 1, find the minimum. Right? That's pretty straightforward. Now where do you put it though? Right? Before I was saying, well, put it at the first spot, second spot, third spot. Where am I going to put it now? Right here, right? Where it needs to be. So place it at index I, right? So what does that mean though, right? Obviously there is, if I go through and I find here's the minimum element and there's already somebody at I, do I throw that guy away? No. What do I mean by take this element and put it right here? What am I going to do with this guy then? I'm going to swap them, right? In other words, swap the minimum element and a sub I. Right? Good? Right? So now that's the ith iteration. Now think about this all as one big iteration, right? Think of that as one thing, right? How many times do I do that, right? So the first iteration, we've got that I is going to be 0, and we search for the minimum I through n minus 1, right? The second iteration, we've got I is 1, and we search 1 through, or 0, I guess, right? Through n minus 1. Right? Dot, dot, dot. How many iterations do we actually go? Well, there are n elements, right? So let's go ahead and advance to the second to last iteration here, where I is now n minus 2, and we search n, or I, 1, we search n minus 2 through n minus 1. How many elements are there? 2, right? And so we find a minimum among these two and place it where it needs to be. Now what about that last element on that last iteration? How many elements do we have left that are unsorted? We've got n minus 1 elements here that are all sorted. And we have this one guy at the end here, a sub n minus 1. Right? If you search an array of size 1 and find the minimum, guess what? Do you need to actually search? No, that's the thing, right? It's where it needs to be. You don't need to go n iterations. You only need to go how many iterations? N minus 1 iterations, okay? So with that in mind, let's go ahead and implement it in C here, okay? We were searching for integers in an array, so let's go ahead and sort integers in an array. It's a void function. I'm not returning anything. You're going to give me an array, and I'm going to selection sort it. Now, is that going to work? I'm not searching for a key anymore, so the key element goes away, right? But should we make it so that the array cannot be changed? No, you are fundamentally changing it now, right? You are sorting it. So let's go ahead and get rid of that, okay? I'm going to go ahead and write my outer for loop. For int I equals 0, I is less than n, I plus plus. That would be the idiomatic for loop that you want to go over every single element. But remember, do we want to go every single iteration here? Nope. We only want to go up to, from 0 up to n minus 2. So n minus 1 here. Why? Because it's strictly less than. Okay? Now what I'm going to do is I'm going to search elements array sub I through array sub n minus 1 for the minimum. Dot, dot, dot. after I've done with that, I will swap whatever the arrays of min index and arrays of I, right? Put it where it needs to be. That means, of course, I'm going to need a minimum index here, int min index. What can I initialize it to? What would be a reasonable assumption? We've got to start somewhere. So if I'm searching among these elements right here, right, where do I start? What do I do to assume that there's a minimum element to begin with? We'll just suppose that that's my minimum element. Right? And then if we go along and find something else that's less, then we'll update this index right here. So where should I start my index? At I. Now, for, oops, move it up there. For int j equals, do I start it at 0? I'm trying to find the minimum element between I and minus 1, the last element. Right? So I don't start it at 0. Should I start it at I? I could, right? But I'm gonna compare the array element, the ith element to itself. Does that seem like I should do that? No. So let's go ahead and start it one extra over there. Right? While I is less than n, that gets me up to n minus 1, remember? Now it is more idiomatic over here, right? Or j plus plus. Oops. J, there we go. I, j, j, j. Okay? Now, if I find something that's less than what I've found so far, if array sub j is less than the array element at the min index, then that means that I've found something even smaller. And so what do? I update my min index to be j. Once I'm done with this loop this inner loop here, I found my minimum element. I found the element at array sub min index. And I need to swap it with array sub I. So that's just a temporary variable. Right? I'll go ahead and take the value in array sub I so that frees it up to place in the value at min index. Right? And now I can go ahead and put it back, put the ith element back into min index equals array or temp. Right? There we go. So I'm just swapping them around. Right? There's selection sort. Right? Let's test it and make sure that it works. I'm going to go ahead and restore this old array right here. Right? And I'm going to go ahead and sort it up here. Right? Selection sort of array n. And I've also added in this print function, or from, I think it was lab 7 actually. We gave it to you. Let's go ahead and print that array before and after. Right? Oops. Just copy this. Print that array before and after. Right? I want to make sure that this is actually working. Right? Demo.c. Okay. Again, ignore those. So, does that look like the sorted array that we came up with? 1, 2, 3, 4, 6, 8, 9, 9. Yep. Looks like it's good to me. Okay. So, now our binary search down here will work. In fact, it was not able to find key 42 because 42 is not in there. Right? Great. Well, what I want to do now is I want to ask the question of how good is this? Right? So let me go ahead and comment out all of this stuff here. Right? And what I've done is I've set up I'm going to set up an experiment here. This is also from Lab 7, where you can generate a random array of a certain size, and it keeps the values small so that you can look at them if you really wanted to. I don't want to look at them. What I'm going to do instead is I'm going to create a new random array, int array is equal to random array of size, where that's being read in from the command line. All right? The default here is 10. Otherwise, we can give it another value. I want 100 elements. I want 1,000 elements. Because what I want to do is I want to benchmark this. I want to see how good this is. Right? And we'll go ahead and sort it. Selection sort the array and size. Right? There we go. And let's go ahead and print it out, at least the small one. Print array, array and size. Right? So let's run this. Oops. What was it called? Print array? Print array, not R. There we go. All right. And if I just run this, it's going to give me a random array of size 10. To prove this to you that it's actually random, let me go ahead and print it before, and let me print it after. Right. There we go. So before, it was just this random, these random values. After, it is sorted in ascending order. Okay? All right. Well, that was 10 elements. What about 100 elements? Okay, well, now it's getting kind of unwieldy because, of course, I'm going to have a lot of repeats. But I'm sure, but visually here, it looks like it works, right? So what I'm going to do is I'm going to take out the print statements so that it doesn't mess up my screen with a bunch of output, right? And then I'm going to run the experiment again, 100. Okay, so that was pretty quick, right? 1,000. That was also pretty quick. So at what point do you think that we can start to notice the performance, you know, in human terms? Like we'll actually see a degradation here. Anyone want to estimate? Let's go with 10,000. Right? Was that noticeable at all? Kind of, a little bit maybe. How about 100,000? Now is it noticeable? Okay. Very noticeable, right? Okay, there, finally, it was done, right? So let's go ahead and kick it down to 10,000. Slightly noticeable. I can use a time utility here to, let's see, time, to report how long that actually ran. And in real terms, it was 0.121 seconds, right? The user time here and then the system time, those are also reported. It didn't actually take 1.2, I mean, in real life, in real terms, in human perception terms, it took this time. But in user time, the program was only running that much on the actual CPU, right? That, you know, it might have been thrashing in and out or something for microseconds or whatever. So let's go ahead and bump this up to 20,000, right? Because we did see that it was noticeably long and we didn't want to wait that long for 100,000. Estimate how long it will take for 20,000. When I bump this up by an order of not an order of magnitude, but I double it, right? So remember over here that when we were looking at linear search and binary search, those are two metrics that we looked at with respect to performance. The linear search here, that if we double it, right, if it took 10 seconds before and we double the input size, what will we expect? About 20 seconds now, right? Because doubling the input size increases the time it takes linearly. That's why we call it linear search. What about binary search? If I double the input size, I'm only doing one more comparison, which is a blink of an eye, right? That's not even perceptible. Right? What about selection sort over here? Well, if it's like linear search, we would expect it to do what? Take twice as much time, which would be 0.24 seconds. Right? Ooh, was that 0.24 seconds? No. About how much extra time was that? Almost about 4 times as big? Right? Even a little bit more? Okay. Well, let's see if that holds. What if I double it again and go up to 40,000? Okay. 4 times as big would be 2 seconds. So why are we getting this multiplicative factor of 4 instead of 2? Right? To understand that, let's go ahead and take a look at selection sort again. Right? So let me here. I should have taken a screenshot or something of this, right? So I'll go ahead and write out some pseudocode over here based on this, and then I'll come back over to it. For I running from 0 up to n minus 2, ... For j running from I plus 1 up to n minus 1, right? Do something. Do something. There we go. All right. So what was the something that we were doing, by the way? Inside this for loop, inside this inner for loop here. Right? Well, we're doing something on line 76, right? And we're doing something on line 77. Do we always do something on line 77 though? No, because if the if statement here is false, this will not get executed. So that's probably not where we want to put all of our attention. What are we doing on line 76 though? We're getting an element out of the array, getting an element out of the array. Great, now we're done. Now we've got those elements, I should say. We're not done. Right? And what are we doing with them? We are comparing them. Right? That was our same standard, if you remember, for linear search and binary search. Here's an element. Does it match that element over there? Here's another element. Does it match that element over there? We were doing comparisons. Now, in that case, we were doing equals equals, right? But in this case, we're doing less than. They're basically the same thing, right? It's not equal, right? It's not equal, and this one comes before that one, or this one comes after that one, okay? So we're doing a comparison. What is that something? That is a comparison. So the question we had with respect to the efficiency of linear search and binary search was all based on how many comparisons are they doing, because comparisons take some computation time. So now, selection sort, how many comparisons is it doing? Right? So let's take this line by line, this simplified version here. How many, 1, 2, 3. How many comparisons do I do on line 3? 1. One comparison. Now, how many times is line 3 executed with respect to line 2? Right? Look at this as big with just one block, right? How many times is this executed with respect to this for loop up here? Well, it's executed when j is I plus 1, I plus 2, I plus 3, dot, 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 until it's n minus 1. How many is that? Okay. I'm going to set up a summation here. For j, running from I plus 1 up to n minus 1, we've seen sigma summation notation, right? Okay, good. All right. I'm doing one comparison. Okay? Solve this summation here. So this is going to be 1 plus 1 plus 1 plus dot, 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 plus 1. How many times? Well, label these things. N minus 1 and n minus 2 dot, dot, dot. This is I plus 1, I plus 2, I plus 3, dot, dot, dot. Right? Those are the indices for which I'm adding 1 each time. If I were to write it out like this, 1 plus 1 plus 1 plus dot, 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 plus 1. If I labeled them as 1, 2, 3, 4, 5, all, dot, 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 up to n, could you answer the question now? How many 1s are there? N, right? So now over here, it's no different. It's just that I didn't start at 1. What did I start at? I plus 1. So let's come back over here and rethink this by putting some extras inside, right? So 1, dot, 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 dot. What if I went up to I, and then I plus 1? That's where I start in that other summation, right? Plus 1, I plus 2, I plus 3, dot, 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 up to, 1, and then I stop short here, and minus 1. So how many total? N minus 1. But these I'm not counting, right? So how many are there? How many 1s are there that I'm not counting? How many are right here? I. Right? Started up way too high. There we go. How many are here? I. So how many total over here? The ones that I am counting. It's just algebra. Arithmetic even, right? How many total? N minus 1. And take off the ones that you didn't count. I. Right? So n minus 1 minus I. I'm going to rewrite that though. N minus I minus 1. Okay? That tells me how many comparisons I'm doing with respect to this block right here. Now, how many times do I do that with respect to this outer for loop here? I do this for I being 0, 1, 2, 3, 4, all the way up to n minus 2, right? That's not that easy. That's not that straightforward. I will write a summation though. For I running from 0 up to n minus 2, n minus I minus 1. Right? What is that equal to? Right? So let me go ahead and copy this. And let's go ahead and create a new slide here. There we go. Okay. Now, I know how to do that first one and that third one. So let's break this up. Okay. So I'm going to break this up into 3 summations. Is this valid, first of all? Yeah, why? Because sum of summations is equal to summation, sum of summations is equal to the summation of sums, right? It's just A plus B plus C. You can do A plus B, you can do B plus C, and then the other one, right? It's associativity. Right? So I'm going to break this up into 3 summations. I running from 0 up to n minus 2 of I minus I running from 0 up to n minus 2 of I. Oh, sorry, 1. Oops. There we go. Now, hopefully we can all do the first and third one together here. The first one is n plus n plus n plus n. How many times? Now, this is where 0 indexing comes in. 0, 1, 2, 3, 4, 5, 6, all the way up to n minus 1, n minus 2. So how many n's would there be? N minus 1, right? If you want to, just start at 1 instead, and then remember that you have to add one more n at the end, right? Minus, and then I still don't know how to do that one. But I do know how to do the third one. 1 plus 1 plus 1 plus 1. Same exact answer as before. How many 1s are there? N minus 1. Which I will just simplify to n minus 1. Okay? All right. So for that second one, though, I'm going to have to bring in this guy named Gauss. And again, this is all this is probably apocryphal. In fact, I think that I know a paper that documents that it's apocryphal. But the story goes that when Gauss was a young boy, that he was bothering his teacher, and he was giving busy work, and the teacher said, "Go in the corner and add up the numbers 1 to 100." And that'll keep him busy for a while, right? But he comes back immediately with an answer of 50/50, right? 5050, right? How did he do it? Well, he just came up with a summation, Gauss's formula. That if you go from 1 up to n of I, right? In other words, you're going 1 plus 2 plus 3 plus ... plus n, right? Then this is equal to n times n plus 1 all over 2. Right? And it's a nice formula that allows you to do an inductive proof. It's a nice formula that comes up a whole bunch of times in algorithm analysis. Why? Because you have a for loop within a for loop, right? And so you're going to have this summation of natural numbers over and over and over again, right? So it's just something to remember, Gauss's formula, okay? In fact, it came up, I was bored over the break, and so I did some more advent of code stuff. And one of them from last year had you doing an optimization problem of moving things around. And then the second part was nothing more than, all right, well, now the cost is different. Now the cost is the sum of natural numbers. And if you knew Gauss's formula, it was an immediate just one-liner change, right? Not only that, but it was efficient because you could use this closed form solution right here, right? If you didn't know that, then you would have ended up adding a third loop within a loop. So 1, 2, 3 for loops, which would have then been, n cubed And it would not have been feasible for you to do that at all. It would, the input sizes were thousands and thousands, and so you would end up doing millions and billions and trillions of things instead, and it would never have computed, right? All right, so let me come back over here and adapt that. Remember, n times n minus 1 minus, now Gauss's formula starts at 1, but if I put 0 in here, does it matter? 0 plus whatever, right? So I'm going to go ahead and immediately change that to 1 so that it matches Gauss's formula. Gauss's formula goes up to n, but we only go up to n minus 2. That's all right. Take n minus 2 and plug it in for n over here. N minus 2 times n minus 2 plus 1 all over 2. What's that going to end up being? N minus 2 plus 1 is n minus 1. So we've got n minus 2 times n minus 1 all over 2. And then don't forget that last value there, n minus 1. There we go. Okay. So simplify, 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 right? That's just basic algebra, and I don't want to, this is not an algebra class. So, or arithmetic or algebra? That's algebra because there's a variable there, right? It's going to end up coming down to something, 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 where you've got n squared all over 2 dot, 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 plus a bunch of other stuff, right? This is the most important term here, right? What about this 2 down below, though? Is that all that consequential? So remember when we looked at linear search? We looked at it from a couple of perspectives. A best case running time, where you got lucky and you found it in the first immediate position, right? An average case, where there was a divide by 2 out front, and then a worst case, where there was not a divide by 2 out front, or 1/2 out front. Did it really matter for that worst case and that average case? They're still both linear. Right? You take your program and your data or whatever, and you move it onto hardware that's twice as fast. What happens out front to that multiplier? It changes based on how fast each operation is. It changes based on how fast each comparison operation is. So I'm going to ignore that as well. Right? I'm going to ignore these lower order terms. I'm going to ignore this constant here, and I'm going to come out to an answer that it's about n squared. Now we're not going to do big O analysis, asymptotics here, but that's the takeaway from this. Right? Now, let's do the same thought experiment with respect to comparisons and selection sort that we did for linear search and binary search. Right? If I have an input size of n, and it takes n squared time, right? Then what if I double the input size? How much time will it take now? Right? Everything is squared. What happens to the constant out front? This is 4n squared. In other words, compare these two. Right? How much larger is it? Or how much more time is it now? No? What was out front before? 1. And what do I have out front now? 4. It's 4 times slower. Right? Hey, that sounds familiar. It's 4 times slower. Right? It doesn't matter what the constants out front were. That if you go up by an order of magnitude, let's see if it still works here. If we go from 40,000 to 80,000, it took 2 seconds before. If we double the input size, that means it's going to be 4 times as slow. 2 seconds times 4 should be 8. 1, 2, 3, 4. You can't do the 1, 2, 3, 4, 5, 6, 7, 8 trick. There, 8.13. Remarkably close to our theoretical analysis that I just ran through, right? What if we went from, say, 10,000? What was 10,000? Right? That's 0.1 seconds. What if I went up to 100,000? Well, while we're waiting for that, What if I went 10 times bigger? 10n. If it took n squared before, what's it going to take now? 10n squared. That's going to be what? 100 times slower. Remember that it took 0.1 seconds. It should be done by now. So if it's 100 times slower, it would be what? 10 seconds? A little bit above that, right? What if I went to, that was 100,000. What if I went up to 1 million? 12 seconds becomes what? Oh, all right. 12 seconds times 100 seconds, 2 minutes. That'd be what? 10 minutes, isn't it? 1,200 seconds. Jesus, why is it not? Come on. Oh, it's Wolfram Alpha is taking forever now, right? I'll go ahead and run it and see if we can get it done by the end of this class. Right? All right. Maybe it's having trouble doing two things at once. There we go. 1,200 seconds. Okay. Divided by 60. DuckDuckGo can do it. 20, so that's 20 minutes, right? This is not going to execute within this class period. But well, wait a second. Did we really give it too much? 1 million things? Is that really too much to sort? Is that big data? No, that's less than a megabyte, right? You can't sort less than a megabyte in less than 20 minutes, right? There's got to be a better way, right? So what's your takeaway from this? Selection sort. Does it sound like a good sorting algorithm? Probably not. Much like linear search, well, I mean, if it's unsorted, then you have to use linear search. You have to be brute force about it. You have to check everything. But binary search had this divide and conquer kind of approach. That it said, well, wait a second, what if you were sorted, we could jump to the middle here, and then we would effectively cut it in half. Right? What if we use that idea to also sort it? Right? What if we had a divide and conquer kind of a strategy? For that, let me go ahead and come over to my pad here, and let's copy that stuff. 4, 9, 3, 8, 6, 2, 1, 9. Okay. There's my array from the original array. Now what I'm going to do is I'm going to split this up into two arrays. The way that I'm going to do that is by selecting this first element here, and I'm going to say, all right, well, you know what? Just like binary search, I want that to be in the middle. Right? I don't know if that's the best choice of what's in the middle, but I'm going to go ahead and put everything over less than it over here and everything greater than it over here. So 9, I'm going to go through the rest of the elements here. 9 is greater, 9, right? 3 is less, so I'll put 3 over here. 8 is greater, so I'll put 8 over there. 6 is greater, so I'll put it over there. I'm getting very lucky here. 2 is less, and 1 is less, and then now I'm done. Oh, sorry, there's one more 9. There we go. Put 9 over there. And now I'm done, and I'm going to put 4 in the center here. Right? What I've done is I've pivoted everything around here, around 4. This is my pivot element. Right? It's kind of like your pivot foot. You keep your foot down and then you can pivot around it. That's your center. And then I'm going to put everything that is less than it over here, everything that is greater than it over here. It's almost sorted now, right? This seems like it should be much quicker. What I'm going to do is I'm going to then recurse on this part because that part is not sorted. I'm going to also recurse on this part because that part is not sorted. But tell me about 4. Would I ever move 4 again? Nope. So it stays where it is. Right? Do it again over here. Choose a pivot element. I'm just going to choose the first one, 3. I'm going to put everything that is less than it to the left and everything that is greater than it to the right. So 2, 1, 3. 3 is where it needs to be. Then I will recurse on the left sublist and the right sublist, but tell me about that right sublist. Is there anything to sort? Nope. Continue, right? I will choose my pivot element here to be 2, right? And so 1 is less, and I'll put it over here. And then 2 ends up where it needs to be. I will recurse on the left and recurse on the right. Do I need to do either one of those, though? No. By definition, a list or an array of size 0 or 1 is sorted. Right? Okay. Do the same thing on the right side. Here's my pivot element. Right? 6 is less, 8 is less, 9 is less, and 9 ends up where it needs to be. There we go. Recurse on this, but do I even have to recurse in that left sublist? It's already sorted. Right? How many comparisons did I end up doing here? Right? Well, every time, this is called partitioning, every time I put something to the right or I put something to the left, right, that's one comparison. So in this case, I had to do n-1 comparisons. But I potentially cut it in half each and every single time. So ultimately, and we're not going to go through the full analysis here, but in the best case and the average case, this sorting algorithm is going to do n log n comparisons. Right? This sorting algorithm does things quickly, and that's why it's called quicksort. Right? It chooses a pivot element and partitions around it. We will not implement this. Because I'm going to show you a much, much better way, right? But there are n log n comparisons here. Let's do the same analysis as before. That if I go from n to 2n elements, with selection sort, it's going to slow down by a factor of 4. Right? How does it slow down now? Again, this is going to be n log n. If I plug in 2n log 2n. Now pull out your algebra skills or your trig skills, right? And your log identities. And what can I do with this log right here? What is log of AB? Log of A plus log of B. Right? So I can split this up into 2. Log of n plus log of 2. This should look familiar because you're only doing one more comparison for binary search when you double the input size. So what happens to this thing right here? It becomes 1. Right? And this is all equal to 2n log of n plus 2n. We're not, so it's not just simply 1, but it is a linear number of more comparisons. Right? But look at these two values here. Which one is larger intuitively? 2n log n or 2n? Well, log n is a monotone increasing function. You can't get away from that. So which one is larger? This one. Okay? How does a circle become a square? Okay, whatever. All right. So let's go ahead and ignore this lower order term here. Before it was n log n. What is it now? It's roughly twice as slow. Hey, that sounds familiar. Linear search is twice as slow. So we're not getting the exponential speed up of performance of a linear search versus binary search, but we are getting a much better speed up. Yeah, keep going. All right. So the question I'll leave this on is, not only is this much better, but how do we implement it? So what we're going to focus on Wednesday here is, what if you wanted to do selection sort, but you wanted to do it in descending order? What would change? This greater than, right? What if you wanted to do it not on an array of integers, but you wanted to do it on an array of books? Right? How would this change? Well, you'd have to look at one of the particular things, like a title or an author or a rating or whatever else we put into those books, right? Do you want to write this over and over and over and over again? No, I don't want to write it at all. Right? So what we're going to do is we're going to generalize this use a quick sort method that's already built into both languages, right? And be done with that for the rest of our lives. Right? We're not going to write, you never ever write your own sorting algorithms in practice. You only write the configuration for your sorting algorithms, right? We do have a guest here, but I will go ahead and stop the live stream. For those watching online, make sure that you're looking at Piazza for the opportunity to earn $25 to engage in some research here. All right, so with that, I will hand it over